John Helliwell has been selected as the 2014 ACA Patterson Award winner for his pioneering contributions to the development of instrumentation methods and application of synchrotron radiation, particularly for macromolecular crystallography. A longtime member of the ACA, we do certainly appreciate that, and a professor of structural chemistry at the University of Manchester, UK. John received his undergraduate degree in physics from York University, where he was mentored by Michael Wolfson and Peter Main. He then pursued a PhD at Oxford under the supervision of Margaret Adams. He was mentored by Charlie Bugg and Guy Dodson in the laboratory of Dorothy Hodgkin and David Phillips, and was involved in the first experiments that used synchrotron radiation for macromolecular studies. So without further ado, I would present the talk, Synchrotron Radiation, Macromolecular Crystallography, Instrumentation, Methods, and Applications. John?
Thank you, Martha. It's a great honor for me to receive this award and to be linked with the name of Patterson. So really heartily thank the ACA for this Patterson Award. In preparing the talk, I looked carefully at the ACA website and I was very struck by the mission statement. Share your science and change your world. And I really feel I share that vision and worldview. We have a cooperative effort. We go back a long way, and probably my most prominent contribution to the ACA was with Steve Ehrlich, with the Transaction Symposium, 2 decades of synchrotron radiation in crystallography, which we organized in Buffalo in 1999 and brought together the Transaction Symposium volume. And of course, this is the current cover of the ACA Reflections. Now, of course, I think you all know Patterson very well, so I wondered quite how to give perhaps an insight which maybe you've not seen before. And I turned to the book Patterson and Patterson's that Jenny Glusker and colleagues brought together. It's a really beautiful book. And near the back are some personal reminiscences. And I picked up one by Dorothy Hodgkin. Patterson obtained a fellowship to go and work with William Henry Bragg in London. His supervisor said that he should alter his ways and work hard to represent the USA well. When he arrived, William Henry Bragg said, of course, besides work, you enjoy yourself. So that's quoted from the book from Dorothy Hodgkin. I love this photo that I found on Google Images of Patterson. He strikes me as a kindly face, lovely photograph. When I was a student, PhD student, which Martha has referred to, I was perhaps a rebellious student. I sensed that what was going on in the lab was somehow rather basic. This was not a popular comment because it was the equal leading laboratory of the land alongside Cambridge. Dorothy shared with me a preprint from Stanford of the work that was led by Keith Hodgson. It was published in PNAS. I got an early copy in 1975. The first sentence says how controversial it was, considering the possibility of using synchrotron radiation in protein crystallography. And it evidently was also controversial in the UK because Ron Mason shared a letter with Dorothy and the head of the Research Council, which Dorothy gave me, pointing out his disagreement with the view that synchrotron radiation would not be relevant. The first reference in that paper is the paper in Nature, Synchrotron Radiation in Biological Diffraction, by Gerd Rosenbaum, Ken Holmes and John Bitts. And Gerd Rosenbaum was here at this meeting. So with these two papers, I could make my own mind up. There was no controversy. This was really important. And so I committed my career, my early career particularly, until I branched out into my own projects, into trying to help make this happen. So I got my chance, although I did an experiment on NINA in 1976. The main chance came when I led the team to establish the Daresbury synchrotron radiation source, protein crystallography station 7.2, the second station on the bending magnet 7. This was a fully tunable design from 1.2 to 2.6 angstroms. And you can see here from the universal curve for the source, there are two marked here, one the bending magnet and a later superconducting Wiggler magnet that I'll come to shortly. And we see these large numbers on the y-axis, and I'll detail those in a minute, for the brightness of the source. And on the instrument, in the commissioning time, I gradually explored various wavelengths, particularly up towards the longer wavelength end, which was especially new, I felt. And this shows a test diffraction pattern from lysozyme, not in a glass capillary, but with the crystal wrapped in a piece of mylar to make a rolled ion capillary, because the glass absorbed too strongly. So the initial SRS was not that well suited to crystallography, especially with its horizontal source size of 14 millimeters. So that's illustrated there, with a large horizontal source size. Vertical was quite good, 0.4 millimeters. So initially, I could get 20 times the home lab rotating anode intensity. That's the rotating anode of that time. It's improved a lot by the manufacturers. But at the time, it was 20 times the best we had in Oxford. And it was fully tunable. The addition of the vertically focusing mirror brought us up to 100 times. And we'd only just started. So this was a fantastic step. But it was still controversial. But we did get our first SRS PX users from the UK and international, the US and Sweden in particular. And I think exciting results. And I think they proved to be exciting. So an early experiment was brought by Howard Einspar. Howard's here. And so he was interested in the p-lectin as a dimer, in which were calcium and manganese in these two closely spaced metals. And it was readily possible to tune to the manganese K-edge, which was accessible 1.816 angstrom. And so with a carefully aligned crystal, we measured the data on photographic film. And in each subunit, we got a very clear indication of the manganese with a bigger signal and calcium around, just slightly good noise for the adjacent peak, and the equivalent result in the other subunits. And we published this in Actocris B in 1985. One of the first, I think, optimized and on-scattering results with synchrotron radiation. Purine nucleoside phosphorylase was brought by Steve Illey, also from Birmingham, Alabama. And that was a project with Charlie Bogue, who, as Martha referred to, was on sabbatic in Oxford in Margaret's group. And so it was an exciting project. It had the challenge of overcoming the 80% solvent content. And from my laser book, you see the crystals, the diffraction, and you see here from the view down the symmetry axis the very high solvent content, but a good quality electron density map from which the trace readily came, the polydense chain. But a proud moment was Charlie's Scientific American article in December 1993. They'd been struggling in the lab, and his comment was, "We eventually filled in the missing details in collaboration with John Helliwell at the Daresbury lab, synchrotron radiation source." Something to tell mothers and fathers about. Charlie set up the BioCryst Pharmaceuticals with this as one of the launch projects, one of the first structure-based drug design companies in the world. Michael Ruslan arrived, and you see Michael and in fact the rhinovirus, which was the crystals he brought with him. And he'd come from Hamburg. This was where he came up with the American method. Now, in the politically correct modern times, this is perhaps not the best statement, that shoot first and ask questions later. But anyway, that's in his paper, it's a direct quote. And here's a very nice acknowledgement to both Hans Bartunik in Hamburg and myself in Dunsbury. To make clear, the data that finally solved this was measured at MacChess, which was established by Keith Moffett. With the success of the first instrument, the superconducting wiggler became a possibility, and so I led the establishment of the instrument 9.6. So here's the superconducting wiggler, which was built by the Rutherford Appleton Laboratory near Oxford, and that of course is where Diamond Light Source is now sited. There's a pioneering step, not without difficulty. This is one of the Series 0 Enrapnonius TD diffractometers, designed and built by Uli Arndt and then commercialized by Enrapnonius. But we did a lot of work as well on film. So in terms of pushing the methods, by now just out was the paper in Science by Keith Moffett, Dorothea Savigny and Don Bilderback on the possibility of using Lauer diffraction in protein crystallography. And we were able to, because of the design, I'd insisted on having the white beam coming into the hutch, and we were able to do tests. This is just a computer simulation, but it illustrates nicely the polychromatic nature of the diffraction. This was a PLET tank, which Howard had kind of left crystals of because it was a radiation-hard crystal, very suitable for testing this approach. But here came a good chance to stimulate chemical crystallography. And Marjorie Harding led a project using particularly the TB diffractometer for working with what she called very small crystals. These were bigger than microcrystals, but it was really an important step for pushing the frontier towards smaller size. Probably most iconic was the virus crystallography that was possible. So from UK, David Stewart arrived with his safety officer with an attaché case handcuffed to his wrist with the foot and mouth disease virus crystals. And here you see the FMDB. This was entirely based on the structure, entirely based on the data from 9.6. Bob Liddington arrived from Harvard. He'd been with me for 6 months at Dahlsbury as a student, and by now was working with Steve Harrison. And this is the SV40, a larger virus than the FMDB. And this was using data measured both at 9.6 and at MacChess. Now, I've stressed that these two instruments were tunable, but they weren't rapidly tunable. Because of the large horizontal source size, I opted for a focusing monochromator that required the beam to track. But in 1985, the SRS machine people introduced a high brightness version of the lattice, and so I was able to install the double crystal XAF type design and a toroid mirror for the focusing. And so the rapid tuning became possible. Now, as a student, I'd been very interested in the phase problem and picked up on this paper by Okaya Babinski in 1956 using 2 X-ray wavelengths. So 3 measurements, 1, 2, 3, sorry, my hand isn't quite steady enough. And Ray Babinski, I picked a picture from Google Images. But with the rapidly tunable design and the case study 5.7, it's the 2 wavelength one, and using a brominated oligonucleotide, we got very clean electron density maps from the phasing. You see here the the base and so on, clearly showing up. Now, by this time, I'd taken a very important career step change and moved back to the university to try and establish some projects of my own, but I still had a joint appointment. And so Andy Thompson was the lead instrument scientist. He'd worked with me from the outset at Daresbury, and I learned just last month that he'd been made head of life sciences at Soleil. This was half funded by the Swedish Research Council. So this was a really quite a high, important step at Daresbury. Now, inspired by Wayne Hendrickson, Alphonse Heidner at Basel University had made a selenomethionine hydroxymethyl violin synthase enzyme. Important enzyme for synthesis of the tetrapyrrole, and that leads, of course, to heme and so on. Wayne, of course, with clarity of purpose, developed the whole MAD method and in a sense, swept aside any efforts certainly that I was doing. The enormous difference Patterson Maps. On 9.5, just to show you one of the Harker sections, compared to the ESRF. The ESRF had introduced a new image intensifier electronic detector, the Jean-Pierre Moy detector. And this shows the high quality of both, but the ESRF map on bending magnet 14, which I believe is the first third generation source MX station, is also very high quality. And that just shows the fluorescent scan for completeness. Chemical crystallography again enjoyed a spin-off. So this is work now led by Madeleine Helliwell, my wife and colleague collaborator, and it shows a zinc substituted gallium, a microporous layout compound, and these are the different 11 wavelength study to look for the small percentage of zinc substitution. So isolating only the zinc, either from the delta F prime or the F double prime optimized, and also deliberately making the zinc contribution smaller just to show the gallium. You can see clearly what's happening with these 8 sites in terms of the partial substitution by 2 of zincs and the lack of substitution of the other gallium sites. So the instrument scientist here, this is on SRS 9.8, very similar design to 9.6, was led by Simon Teat, who's now at ALS in Berkeley. The point about these sort of experiments, which are with the National Institute of Chemistry in Ljubljana, Slovenia, led by Slavko Kaučić and Natasha Zabukovic-Logar, is to enhance the catalysis of these compounds and the precise information of the metal atom substitution to tailor the catalysis is important to them. The commercial activity was an important aspect of the SRS, and crystallography, and protein crystallography in particular, led the way. When the SRS closed in 2008, the government commissioned a social and economic impact study of the SRS, and this volume is available on the web. If you have trouble finding it, email me, I'll give you the copy. The point being was that to serve industry with analytical and research technical services is important, both for the UK PLC, but also was something that the politicians grasped immediately as a way of explaining to taxpayers the spend on such an obviously large instrument tool. And it was approximately £300,000 income to the SRS every year. Elizabeth McLean, Pierre Riscala and myself wrote a summary in 2005, 2006 for the Pharmaceutical Review on this industrial usage. Elizabeth McLean now heads up the diamond light source commercial darts type activity. It's not called darts now, it's not Daresbury. Now let's take an overview for a moment. The key things for me and also for the field. So in '76, my initiation was with Joanne Bordas, my local contact, and my first experiment on MENA. We had 1981, the Raspberry SRS came online, and the first two instruments I've told you in detail about, a little bit about 9.5. But from Stanford was coming the idea of new rings. And so here's one of the front covers of the workshop booklets using the PEP, high energy physics storage ring, a very large circumference ring. And in Europe we had a debate amongst the countries and scientists for a European synchrotron radiation facility as a third generation source. The design, the universal curves, showed colossal increases in intensity over what we had at Raspberry. And from the X-ray undulator, invented in the Soviet Union, I believe. And the immediate and obvious question, much the same as the X-ray laser now, would the sample stand it? So here again, the universal curves, and these larger numbers on the y-axis have become even larger, so we're up to 10 to the 20 here in the brightness, photons per second per square millimeter per milliradian squared per unit bandpass. And these are the numbers at the time of the concept of ESRF. They've improved greatly since. So you have their Benny magnet, their wiggler, and the undulator in its spectral lines, but these then are the trace that you alter the magnetic gap. And these are major gains over the wigglers. And you've got the first harmonic, the third harmonic, and we debated in the Machine Advisory Committee, by which time I was representing the Science Advisory Committee, about the higher harmonics. And so the SRS was somewhere down here, and of course the rotating anode somewhere down here. So this is what I call a colossal increase in intensity. So with Keith Hodgson and Britt Hedman, we got the NATO Collaborative Award to do joint experiments at Stanford and at Raspberry. And how to mimic the monochromatic undulator intensities to test would sample standard. So by harnessing the SRS Wiggler white beam, we could enter the regime where that was true. And here you see the PNAS paper we wrote up, protein microcrystal diffraction and the effects of radiation damage with ultra-high flux synchrotron radiation. And so this is on a gram side in 20 micron test crystal, and the clear and ready diffraction from the sample told us immediately that things were going to be basically okay. It didn't mean that we didn't have to understand better what would happen with the heating possibility or the radiation damage that might be possible. Now the Lowry method I referred to earlier was an initiative taken by Keith Moffat, and I decided this was important, and with Derwent Cruikshank, who was working with me by that time, recently retired from UMIST in Manchester, we joined with Keith on this. And Keith also had the vision for the possibility that a single bunch, sub-nanosecond bunch of X-rays from the ESRF or the APS would allow measurable diffraction. So here was the possibility of nanosecond time-resolved proton crystallography. And here you see Derwent, myself, and Keith looking at younger, obviously, outside the York University Physics Department. And on the front cover of Physics World, this just illustrates a bit of interesting history. Lawrence Bragg took the view that the Lowry patterns were too difficult to interpret because of the multiplicity problem. But when we analysed that, and we were backed up obviously quite readily with computer simulations, so we had a much easier job than Lawrence Bragg, let's put it that way. Then the pattern has a large proportion of singlet reflection contained Lowry spots. So obviously needing wavelength normalization, but a lot easier to manage than Lawrence-Bragg anticipated. Now, the Lowry method I mentioned used initially for benchmarking high intensities, but we could also readily benchmark sample perfection. And so, by now the US was very engaged with microgravity protein crystal growth. Crystal grows like the environment, but convection-free, sedimentation-free crystal growth. And I came in, Charlie contacted me for the characterization of the samples, both grown in microgravity and on the ground. Particularly with Eddie Snell, who by now joined as a PhD student, well known to you at the ACA, and later by Vivian Stoyanov. Gloria, I served as a consultant, and then Titus, another PhD student. We embarked on a whole program of doing protein crystallization and crystal perfection assessments. So here is a simple illustration this is a crystal to detector distance of 2.4 meters on 9.5. Just tapes a film cassette to the wall of the hutch, and there's a very well-preserved diffraction spot over that long distance, and the earth-grown control showing the smearing up to about 1 millimeter. So this is 0.2 millimeter and 1 millimeter showing the mosaicity smearing. So the point about this, I take, I really felt that the microgravity research has given a new vibrancy to an understanding of crystallization and also benchmarking the limits to crystal quality that are possible. And I think has inspired the other sedimentation-free methods of gel growth and microbatch under oil. But that's just a personal view. Other people would say perhaps they have their ideas in a different way. We conducted many studies to validate the Lowry method and the Darsbury software. So with Zygmunt Derewenda, who's here, we were colleagues at York, he provided a mercury derivative of alpha amylase, and we measured Steve Harrop, now in Australia, myself, we measured the Lowry data and processed with the software developed in Darsbury with the computational group. And you see here just a simple illustration of the high quality difference Fourier map showing the mercury. With Anders Lilius in Lund, Martin Lindahl, his postdoc, we measured Lowry data on carbonic anhydrase. You see the metal and the 3 histidines, and we could readily pick up the bound water molecule at the fourth site of the metal, the zinc. And then with Dora Gomez, a PhD student who joined me from Merida in Venezuela, who's here, and a chlorine-containing compound. The Lowry data, we could see from the chlorine anomalous signal the correct hand versus the incorrect hand from the R factor test. The flat parameter not available at the time. And so, again with Alphonse Hadner, we were able to do our own time resolve study using the ESRF by now and the Darsbury-Lowry software. With the JP Moy detector, it was much easier to measure the Lowry data, which would be very tedious with the film and the darkroom, and we got high-quality electron density maps. And so by introducing substrate by the flow cell, developed by Al Wyckoff at Yale, and we used that basic method using different time slices of the Lowry diffraction, T0, 7 seconds, half a minute, 1 minute, 2 minutes, 4 minutes, up to 2 hours. We were able to see the progression with time at the enzyme active site of the growth of the electron density towards the tetrapyrrole that was the chemical reaction for the enzyme. This was a mutant of the enzyme which deliberately made the reaction slower to isolate the second, the dipyrrole of the enzyme reaction mechanism. But more spectacularly, Keith used the Lowry method, and this was to stress this is a totally different software that he and his team developed in Chicago, and Zong Ren in particular. did the nanosecond protein crystallography with carbon monoxide myoglobin, and then later with PYP, phosphoyellow protein. And so with Michael Wolf at TSRF on ID9, this shows the carbon monoxide myoglobin, carbon monoxide here, red negative, blue positive. There is a movie here, but I don't have time to show this in these Keats results anyway. But look at this here. We've got 1 nanosecond time frame. I just find that astounding compared to what we were thinking of when I was a PhD student. The Lowy method and the Darsbury-Lowy data processing software were enthusiastically taken up at the Grenoble neutron reactor source. And here you see Dean Miles now at Oak Ridge, Matthew Blakely, our joint student, and use of the Lowy diffractometer that was installed on the Grenoble reactor. The largest unit cell that we work with, 168 angstrom, but it is body-centered, so let's say primitive 120 angstrom. We got good quality diffraction, and so this whole use of more efficient use of the emission of the reactor that the Lowy method gives, instead of monochromatization, which obviously throws away a lot of the available flux, addresses this major problem of the neutron beam, which is low flux. So it's a beautifully tailored method to what we want to see for full structure description, but it has this low neutron flux. So here is the NBL European Molecular Biology Lab Lowy diffractometer that designed and built and installed at the ILL. It's a neutron-sensitive image plate, initially donated by Nobuo Niimura from Japan. And we use a typical neutron beam wavelength range, 2.7 to 3.6 angstrom. The longer wavelength gives us the increased scattering efficiency, which also assists the low flux of the neutron beam. And here you see one example of a very nice, clean neutron Lowy diffraction pattern. So in the X-rays and neutron game, just to perhaps say the obvious, we have here the X-ray atomic scattering factors, steady increase with atomic number, hydrogen and deuterium are the same. In the neutron game, the neutron scattering factors are much more equal in magnitude throughout the whole periodic table, and of course they change sign. So hydrogen is negative and deuterium is positive. And in particular, the deuterium scattering is as strong as carbon. And so with more modest diffraction resolution, let's say around 2 angstrom, with the deuterium we can see the protonation states quite clearly of the ionizable amino acids and also the bound solvents. So with my own project's development that I mentioned when I made the career change that I referred to earlier, the concanablin A, which we'd also done developments linked to the p-lectin, also allowed us to do the studies at ultra-high X-ray resolution, and this was done actually at MacChess during the sabbatical I had there, and actually Deacon as well, PhD student now at Stanford. And this just illustrates the chemical crystallography accuracy using bond distance analysis. So we have the typical way of representing the bond distance but with the sigma in the brackets, and we can see the short bond, the long bond in these 2 amino acids, the aspartic acid 28, where it's protonated and where it's deprotonated in the glutamic acid 8 case. To find ways of actually introducing the descriptor of the standard deviation on bond distances preoccupied Durwood Crochenk, and he introduced the diffraction precision index for when the resolution was not as good as these values. And I think that's an important step which I'm trying to carry forward since Durwood's death. Now the neutron studies were possible with the Conne system as well, because they made big crystals. And here you see an example of histidine, where we've got the deuterium on this nitrogen and also on this nitrogen, but in this other histidine we have the deuterium here, but not on the left-hand side one. Sorry, the laser pointer's getting a bit weak. And so the bond distance analysis for the protonation of the histidine around the ring is too difficult for X-rays. The bond angles are better, but a modest diffraction resolution, which may be called the typical one, then the neutrons are much more effective at giving the protonation states. There's a very nice review by Matthew now, who's leading the Laddie in Grenoble, that he wrote for Crystallography Reviews. Now, a final highlight is marine coloration in Lobster Shell. And this was a curiosity-driven project led by Peter Zagalski at the University of London. And it will be familiar to you restaurateurs. Here's the live lobster, blue-black, and here's your cooked lobster on the dinner plate. Naomi Chiang, our collaborator in London, grew crystals of the complex known as beta-crystocyanin, which is rotating on screen. I've been joined by a PhD student from Padua University, Mike Cianci, who's here, and also Andrzej Olzak from Poland. The linchpin of getting the structure was the apo-crystocyanin A1. There were many sulfurs available in this protein. So by going back to station 7.2 and using 2 angstrom wavelength as a convenient value, we had to unmothball the instrument for this, which by then had been declared unproductive. We explored getting the disulfides from the data, and by a stroke of luck we also got xenon high pressure derivatives, so they're shown in cyan here, the binding sites, and there's a twofold axis coming out of the screen towards you. And using 9.5 we got very high redundant data for the disulfides to be clear, and the xenon L1H was perfectly suited to the 2 angstrom wavelength. The referee contributed something, who insisted on not letting us call it soft X-rays, so we had to compromise with softer X-rays. 9.6 provided the data for 1.4 angstrom high resolution for this APO A1. We used that as the molecular replacement model for the beta-crystocyanin, which had a high solvent content and diffracted to about 3.2 angstrom. So the answer to the question, why does a lobster change colour on cooking, is to do with the way in which the active carotenoid, astaxanthin, 2 of them are shown here in black, are held both geometrically and electronically. And so the cooking denatures the protein and releases the geometry and also the electronic environment in which the carotenoid is held. The beta-crystocyanin is 40 kilodalton dimer, which sits in a 320 kilodalton final alpha-crystocyanin complex. And that accounts for the final 50 nanometers of the bathychromic shift. The beta-crystocyanin has 100 nanometers. We do not yet know the mechanism for the final 50 nanometers because our efforts, Naomi in particular, to get well-diffracted crystals has not been successful so far. The beta-crystocyanin crystals are a beautiful blue. That shows you the 100 nanometers shift. Madeline led a whole series of carotenoid crystal structures, and actually I'm missing a slide of one of her crystals of astaxanthin, but it's basically the same colour as the cooked lobster. I never appreciated how the public would show interest in this project. There were articles in the Times, the Guardian, the Independent also the radio, the TV, Scientific American, New Scientist, Physics Today. My favourite was from the Liverpool Daily Post, Solution Cooked Up to Red Lobster Riddle. And just in here, you see, or might see, the words that the boffins in Cheshire have solved the question. I confess to like being called a boffin. So in terms of research directions for today, I've just chosen a snapshot of some of the advisory committee work that I've been engaged in. So at APS, here's my brass plaque from Murray Gibson thanking me for 5 years of service on the SAC. It was a great privilege to work with Wayne and others on the different CAT assessment of their projects and progress. I'm chairman of the SAC of Alba, the Spanish synchrotron that Joan Bordas led the charge to establish, and now is led by Caterina Biscari. And at Diamond, I'm on the Long Wavelength Advisory team, and I chair the ESS and Neutron Macromolecular Crystallography Scientific and Technical Advisory Panel. So what do we have today? We have Petra 3, I think, is the most brilliant, most bright, and it's going towards this, what we call the ultimate storage ring. And also soon will be the NSLS 2 and the Max 4 in London. For UK, Diamond Light Source is a cutting-edge source, and it has a vibrant research and development program. From the SRF work, which splendidly led the development of that project, and David Stewart is head of life sciences at Diamond. Alba likewise is a cutting-edge synchrotron source for Spain. ESRF has an upgrade program to produce nano-focus X-ray beams, and the APS is also at an advanced planning with its upgrade. We have the new kid on the block, the X-ray laser. Serial femtosecond crystallography is very active, led by John Spence and Henry Chapman. And we have the overall vision of the single molecule diffraction that has been led by, from the outset, by Janos Haidu in Uppsala. I think an interesting, how to try and contribute to this new area, I think it's interesting to consider the possibility of nanoclusters of molecules as an intermediate step between the nanocrystal and the single molecule. For the neutron sources, we have a galloping development of the megawatt spallation sources at Oak Ridge and at Lund in Scandinavia, and also the J Park in Japan. At ILL, we're seeing optimizations of the neutron guides, the detector, the neutron sensitive image plates, how we read them, and also the positioning of the Larry diffractometer closer to the reactor. So compared to when I was chairing the beam time committee in Grenoble for the LADI, we're seeing measuring times 10 times quicker than at that time. So what was a 28-day allocation of beam time is now 3 days. So things are really moving, I think, in the neutron macromolecular crystallography area experimentally, and I was at the workshop yesterday morning seeing the efforts being made to provide the software tools for the data and structure interpretation. So I've tried to do acknowledgements through the talk, but I'd just like to say overall a hearty thank you to all my PhD students and postdocs over the last 35 years. Also to thank Daresbury Laboratory and the Universities of York, Oxford, Keele and Manchester. And as well as Daresbury, there have been many experiments at different synchrotron and for the neutrons mainly ILL, but other ones, other facilities are coming. So I thank them all for their collaboration. My wife has featured firmly in 2 of the different studies, but without her support and the support of my family, and the amount of travel and so on that I've done, I've really come to achieve what I've described to you today. Thank you to my wife. Beautiful picture of Patterson. Thank you.